his lunch. Everyone invite him for lunch. So he realized that the shear angle is very difficult to find. Okay, it's very tedious experimentally. So he tried to predict. Okay, so I'm going to show you how the prediction happened. Okay. So this is what we call analytical model in manufacturing. Okay, because we use the shear angle to do optimization also. Unfortunately, because of time, I can't show you some like real life example. But if this lecture is face-to-face, somehow face-to-face time pass slower. I can teach more. I don't know why. But anyway, so that's where Merchant came up with Merchant's theory. To predict shear angle. Okay. So his model come up with the shear angle is equal to pi over 4 minus by beta over 2 plus by alpha over 2. Okay. So why I'm doing this with you guys is because in order to use any model, we have to understand how they derive it. Okay. In any manufacturing model that you are going to use in the future, these are all predictive model, not reactive. We need to know the assumptions. And the assumptions sometimes lead to simplification. It's okay. Okay, it's okay. If the assumption lead to simplification, it's okay. Okay, but we need to know what they are. Okay, so what are the assumptions that he made? Now, these assumptions are made to simplify the math. Okay, or not, it gets too complicated. Okay, so the first thing is 2 is infinitely sharp. Okay, that's the first one. The material is isotropic. So same direction in any direction. So you cannot use this for carbon fiber. Okay. So deformation occurs in a plane and not zone. Okay. So remember we talked about primary shear zone. You call it primary shear plane. It occurs in a plane. The cutting process is steady state. So what it means is undeformed or deformed chip thickness is constant. So the shear angle is constant. If the deformed chip thickness is changing, right, we just derive pi, yes or no? If it's changing, the R ratio will change. Okay. And the two big ones, okay, the two big ones is the friction angle beta, right, will remain constant, right, will remain constant and is not affected by temperature and stress, but is based on the combination of two-stroke workpiece material. And he's right. Okay, the friction angle, right? If you look at the friction angle, is in fact friction, coefficient of friction. It's depending on the two mating material. Okay, and the last assumption that he make, which I'll write on this side, the last assumption that he make is that the shear angle pi, right, will orientate itself such that Fp will be at its minimum. So this is like all of us, okay? Minimum work assumption. Right? Okay. Minimum work assumption. Okay. So these are all the assumptions that he has made. And then he looked at his circle. Okay. And he's going to derive an expression that I'm going to work out with you now. Okay. So the two big one is the friction angle is constant. And the other one, the shear angle pi, is also will orientate itself such that Lp will be at its minimum. Okay. So from here, we try to relate Fp and Fs. Why Fp and Fs? Because Fp is because of the minimum work. Fs is because of the shear angle. Right? The shear angle is trying to relate Fp with Fs. Okay. So Fp and Fs, the only similar thing about Fp and Fs, it shares. Okay. Fp and Fs. Wait. Sorry. He tried to relate Fp and Fs, and as I said back earlier, Fs is controlled by the shear angle. Fp is not, right? Fp is determined experimentally. Okay, so the only thing common about Fp and Fs, so Fp and Fs share the same resultant force. Right? So they share the same resultant force. Okay. So he write up an expression. Okay. So if you look at here, so Fp is equal to R. So this is this triangle I'm focusing on now. Okay, this triangle down here. Okay. So Fp is equal to R cosine theta minus alpha. Okay. I'm going to call this equation number 1. And then the next one, he's trying to relate Fs now to R, right? So Fs is equal to R cosine pi plus by beta minus alpha. Equation number 2. Okay. So we are going to deal with where we can put, somehow we can substitute R into one of the expression over here, right? So from equation number 1, right, R is equal to Fp, right, over cosine beta minus alpha, and we can 1 over cosine, we can call it Fp secant beta minus alpha. Okay. So equation number 3. So we can substitute 3 into equation number 2, right? So we have Fs is equal to Fp secant beta minus alpha cos pi plus by beta minus alpha. Okay. So once he have this, okay, he wants to relate the shear stress. Okay. So he would like to find, I think I can get rid of this. I think I've seen enough of this already. So he want to find the shear stress acting on the shear plane. So shear stress is equal to Fs divided by area of the shear plane. Okay, where As is the area of the shear plane. So area of the shear plane As is equal, we derived this last week. All right. So the shear stress, he come up with the shear stress is equal to Fs, which is equal to Fp secant beta minus alpha cos pi plus by beta minus alpha divided by P omega sine pi. Right. So keeping this in mind, this is minimum work. Right. Right. Remember we talked about Fp, the orientation of shear angle such that Fp is minimum. So he wrote down that Fp is equal to the shear P omega over secant beta minus alpha cos pi plus by beta minus alpha and sine pi. Okay. Based on his assumption that he made, right, this is a constant. Shear rate angle is also a constant, right? So these are the only changing terms. So this term will not change at all. And if you were to see no, I just rub off the equation. So let me see, we are trying to prove that pi is equal to pi over 4 minus by beta over 2